So, welcome everyone back to our workshop on perception, planning and navigation. I welcome everybody to the second half. We had now our spotlight presentations and outside there's still the poster session going on. But nevertheless, I think everybody grabbed his or her coffee, got re-energized, and now we are starting the second half of this workshop. We will have 3 presentations. And the first presentation, we have a professor here from the George Mason University, and we will learn about what is learning and planning and control for especially extreme vehicle mobility. We welcome Professor Xiao, big applause, and give him the next 25 minutes to tell us about this research.
All right, thanks, Johannes, for the nice introduction. Hi, everyone. My name is Shi Xiao, assistant professor at George Mason in the US. So today I'm very happy to talk to you all about our recent work on learning, planning, and control for extreme vehicle mobility. So first of all, why extreme vehicle mobility? So our lab started out working on lots of problems in terms of disaster robotics. So for example, we deployed modular snake robots in the Mexico City earthquake. So we developed locomotive reduction techniques to autonomously drive this extreme locomotive, a snake robot, hybrid locomotive, to different places autonomously. And also in the middle, you see the MV unmanned service vehicle, which is a robotic boat. So we paired this unmanned service vehicle up with an unmanned aerial vehicle, in the sky, so that with the visual feedback, we will be able to navigate this unmanned service vehicle autonomously to drowning victims during the Greece refugee crisis. And also on the right-hand side, you see that the Fukushima Daiichi nuclear disaster decommissioning task, where people tele-operate padbots to decommission the nuclear hot zone. So what we did is we replaced the secondary robot with an autonomous tethered aerial visual system on the bottom right. So the drone is flying around with a tether to provide the tele-operator of the ground robot with aerial visual systems. So the tether provides power, provides safety, and it's also a very good mechanism to retrieve the vehicle when the mobility fails in the field, because we really are working in extremely difficult environments. So, but I'm not going to talk about this in today's talk. So I will structure today's talk in 2 orthogonal different directions here. So first is trying to learn to enable high-speed off-road navigation, as shown on the left. And the second is what we call wheeled mobility on vertically challenging terrain, shown on the right. So let me jump right into the first direction, so high-speed off-road navigation. The first word I want to briefly introduce is called learning inverse hemodynamics. So the objective is pretty straightforward. We want to navigate the mobile robot to track the reference trajectory during deployment as quickly and as accurately as possible. This is to minimize the cost function J in terms of total time and also the accuracy of trajectory execution. But the difficult thing here is you need to do this in off-road terrain. This terrain are unknown to you before you deploy the vehicle. So that's why you need to enable extreme vehicle mobility, considering the disturbances from all these terrains. Putting this under a very classical control paradigm here, you have the trajectory to track, with the controller issuing controls to move the vehicle in terms of forward hemodynamic function, and then your vehicle state will change, right? As I mentioned earlier, there's this worst state from the terrain, which is unknown a priori the mission. So, and also this unknown terrain won't be modeled analytically beforehand. So that's why we are using machine learning to deal with this. So our approach here is learning to learn an observation function called G here, which will produce an observation called Y. And then we design an all-terrain model to cover all different kinds of terrain conditions on our observation field. So instead of taking into account this unknown worst state W as we introduced in first, now we are replacing it with this very tangible, very concrete observation Y here in our approximate inverse hemodynamic function as the diagram. So what is our Y? In the first word, we use IMU to enable the observation. So we use this IMU on board the vehicle, and for this autonomous steering vehicle, the action space is the throttle and steering command for high-speed off-road navigation. And we put the last 1 second IMU into our encoder, observation encoder. That will give us our 2-dimensional embedding. And then we concatenate this embedding with our velocity, desired velocity, desired space change from a global planet. Feed both into our learned hemodynamics model, and then it will produce our action, the velocity and temperature, or the steering and throttle command to be executed on the robot. So how does it work on the robot? This is a video showing the high-speed off-road navigation performance using our learned inverse hemodynamics model. As you can see, there are a lot of disturbances from different, terrain. For example, you have some grass, tree, like leaves, tree twigs, also roof, and also high friction pavement and everything. So despite the disturbances, you can see the vehicle is driving at a very high speed, but still maintaining a very high accuracy here to the reference trajectory. So this is the power of learning the IMU IKD. So we also compared our learned IKD on off-road terrain and unseen indoor environment here. So this is the more easier, so homogeneous terrain in a living room. So those are written for. As you can see, using the same model learned outdoors on off-road terrain, which have never seen the indoor terrain at all. Now it is able to also produce more successful, higher speed, safer navigation in an unseen environment. So to give you an idea how our experiment goes, those are 10 different speeds from 1.6 meters per second all the way to 2.5 meters per second. We compare 3 different methods. So green is our IMU IKD model. So red is the baseline we handcrafted, usually designed for low speed and also for homogeneous terrain. Right? So we also have a population model, so showing blue here. We use the same training set, but we remove the dependency on our population Y here to see how important Y is. So, and also all these little circles as you turn from turn 1 to turn 8 to indicate how many times the model failed the turn, meaning either colliding with the track wall or getting stuck. So as you can see, with slower speed, all three models are pretty consistent, but the red trajectory deviates the most from the reference trajectory showing blue in the middle, and the green and the blue are relatively close. Now with increasing speed to the right and also to the bottom, you can see all trajectories start to spread around, meaning they are less consistent. But still, the green is the closest to the reference trajectory and has the least variance. And you can also see the smaller size of all the green circles at all turns, meaning our model fails less frequently compared to the baseline and also the operation. So some numbers here for error bars. So a lot of bars here, but the take-home message is the shorter the bar, the better. As you can see, lots of very short green bars, meaning our model is better than the blue and the red, the baseline and application solution. But I want to point your attention to one set of bars here, which is this turn 8. So in this turn 8, our bar is the highest. So green bar fails the most compared to the blue and red. The reason for this is at this turn 8, the vehicle is transitioning from a low friction grass environment into a high friction pavement terrain. So the model, our IMU IKD model, learned because of the responses from IMU due to the grass. It knows it will be lacking friction, so it learns to oversteer to compensate for the lack of friction. However, due to acceleration latency here, when it's just entered this high friction pavement, so the suddenly increased grip between the wheel and the pavement will cause it to turn too much and collide with this inside the walking route. So this is the problem why our model is not performing well in this transition. This motivates us to enable anticipation in our model. We want to anticipate what is coming next. To anticipate the future terrain can help us to compensate our acceleration latency here when we are doing extremely high speed navigation. So this brings us to our second work on learning visual inertia IKD. So VR IKD. So in addition to the IMU 1-second inertia history, we are also feeding in the upcoming terrain visual patterns. And then combining them together, we'll be able to enable faster navigation with terrain anticipation and can deal with this transition from gravel to grass in a better way. Without anticipating it gets stuck, while if we are using both vision and inertia together, it is able to finish the entire route at a very high speed and without stuck anywhere, without collecting with any obstacles. So the IMU IKD and then VR IKD work now can address this transition between different terrain surfaces. It works pretty well. But we also want to ask the question, is this single-step visual anticipation in an inverse heliodynamic setup really sufficient? So there's some limitation of applying an inverse heliodynamics model because if you only think about one step, you want to get there, what action you should take now, right? So sometimes, when you're doing high-speed navigation, it's more than just simple latency compensation. Sometimes, if you're driving too fast, it may just be too late. For example, when you go very quickly and without stopping, braking earlier, you may actually experience that. Too bumpy, damage onboard components. You may roll the vehicle because you are taking a too aggressive turn. And as well here, on a low friction surface, you may slide in the vehicle all around because of drifting. And you may collide with obstacles or maybe even falling off a cliff. Those are very bad. And those are the things we need to think about in a multi-step forward heliodynamic setup. So no longer single step, no longer inverse. So with this, I would like to introduce our recent work on CARSOR, so confidence-aware high-speed auto navigation. So instead of reasoning only about two consecutive states, ST and ST+1, we need to go back into history and think about the multi-step forward hemodynamics here. So our state is also 6-dimensional instead of 3, because we are doing high-speed navigation. The vehicle is not only moving in ST2 anymore, now it's just moving in ST3. We have our same control input, our steering and throttle command. And we are now, instead of inverse hemodynamics, we are talking about forward, right? Given current state ST, given EP, what is the next state, ST+1? And of course, we are still doing auto navigation where we need to read about the environment. And there's other things we need to consider here, mark as this question mark. So we know we can consider IMU, right, in terms of IMU here. And we know we can consider vision, as we talked about in VRIKD. And because we are doing it at a very, very high speed, another important thing we discovered is we also need to consider speed here. So this is something very important. We will show you why that is the case in our experiment. So by combining all these together, so we will have a representation of the environment, considering VSI, vision, speed, and inertia. And we can use them whenever any of those are available, right? So then that is our forward hemodynamic setup. So with this, I want to introduce our terrain representation for auto navigation on the train approach. So taking the 3 sensing modalities from inertia, you know that, in our IMU, ITD work, same thing. We also need to consider vision, like the upcoming terrain. Here, we also apply a technique called viewpoint invariance. So if you have the same patch of terrain, you may be able to observe it from different viewpoints. But that's still the same patch of terrain. So it's clear that it's response won't change that much. So we are trying to enforce these two are the same, even though they look differently from different viewpoints. We also augment our vision with speed, because that is extremely important for us to talk about what is the response on this visual patch. Only if you look at the visual patch, does not help you using about dynamics. You also need to consider speed. Then with all these things together, we train our self-supervised training model, we have a vision speed encoder. We also have an inertial encoder here to give us 2 different embeddings. So actually 3 different embeddings. So side ES for the 2 viewpoints, 2 of them, and also side I for the inertia. Then we use a self-representation learning loss, which is a bottle point called BL, to minimize the difference between the 2 viewpoints, augmented by speed, and also the difference between the first viewpoint and speed with respect to the inertia, and the second viewpoint with speed with respect to inertia here. Now we are minimizing this bottle point loss. This is our self-supervised shown representation learning set. After we learn our vision speed encoder and inertial encoder, we freeze it for our downstream hemodynamics learning task. Then we train our downstream EMP to think about what is the next step, so what is the roll angle, bumpiness, and sliding, so that we can enable competence awareness, what we have to do next. So some numbers here to show you how good our model performs. Like we compare against end-to-end learning without using any machine learning. We also compare against another state-of-the-art representation learning method called Sterling, but Sterling does not consider speed representation. So that is the key here for us to enable high-speed auto navigation. Here, we show the loss, the downstream training loss, the hemodynamics modeling loss, or error rate, using 3 different representations. So using I, VS, and VSI. As you can see, VSI performs the best if you consider all representations, but you can also, if you only consider I and VS, that can also give you a pretty competitive training loss here. Lower part is the more qualitative, illustration of how the model predicts the next, for example, roll angle. Green is the point prediction, and the blue is ground truth, while red is the Sterling without considering speed. You can see for roll, and also for sliding, and also for bumpiness. In all 3, the green line is closer compared to the blue, while the red is less accurate. So we put this into the motion as well. So in this is called human console, which is a human autonomy shared control center. So human is driving the vehicle, but the console is working in the back end, trying to take over the control when the vehicle is about to break its competence-aware metrics. So when the vehicle is driving too fast, entering this rocky patch, console takes in control and slows the vehicle down. When it is about to slide, console can adjust the steering and also throttle command so the vehicle can stay stable. As well as here, when the vehicle is about to roll because the human is taking too aggressive a turn, console also take over to correct the throttle and steering command so the vehicle can smoothly maneuver through this high friction pavement turn as well. So looking under the hood, what is console doing? So the top row is the human throttle and the human steering, showing dark blue and dark yellow. And the console is working in the background. Like the shaded lines are the actual commands being monitored by the console and sent to the vehicle. As you can see in bumpiness, when it's about to enter this rock patch, so console takes over and reduces speed drastically so that the vehicle won't bump too much. In the second column, you see the vehicle is about to slide on grass. So console not only reduces speed, but also adjusts the steering angle so the vehicle can slide much less compared to without console. So is the last one. So the vehicle is about to roll because the human is taking too aggressive a turn on high friction surfaces. And console is again reducing the speed as well as the steering angle so the vehicle is more stable. You can see the very small peak on the angle compared to a large red peak on the lower right. So we also combine console together in an autonomous navigation setup. This is the MTBI planner. So we put it with console to constrain the confidence awareness metrics. So we want to first see how console compare against without console. So our top speed of the vehicle is 4.8 meters per second, which is pretty fast for a 160 kg vehicle. So what we see here is in console, the top speed and average speed are reduced because console is also paying attention to confidence awareness. So on the other side, you can see much better confidence awareness metrics compared to without console. We also compared against Sterling, another stage representation learning without continuous speed, and also another high-speed off-road fixed-off navigation approach by Li et al. And as you can see, console achieves the best confidence awareness metrics against the two. So we also want to look at hey, how slow you have to drive to achieve the similar confidence awareness metrics compared to console when driving at full speed. So the answer is 3.4 meters per second. We need to reduce our full speed from 4.8 to 3.0 meters per second to achieve comparable confidence awareness, meaning like small bumpiness, slightly low angles. And we also put console on our slow, more conservative planner. And the result here shows console does not reduce the top speed and average speed that much. Meaning console is not just blindly slowing down the vehicle for safety. It's only slowed down when it is absolutely necessary. So that's why console is going to be helpful to enable high-speed navigation while enabling confidence awareness. So this wraps up our first direction for high-speed off navigation. So the second direction I want to talk about is called wheeled mobility on vertically challenged terrain. How do we enable vehicle mobility to drive over obstacles which are of the similar size of the vehicles themselves? So with this, I want to introduce our Mobility with Us project, which is an open source project for both hardware and software. We built a few of these and open source all of these. We have a 4-wheeler, as you see in the video, and this is our 6-wheeler. And recently, we also introduced another 4-track version of the vehicle, also plus a track control system that allows us to study wheeled mobility on vertical challenged terrain with different morphologies, different physical environments. We have a fleet of those that we can study dynamics on those challenging environments. So putting this in a more mathematical, like a more rigorous mathematical formation here, this is the classical 2D navigation system we're dealing with. We have a 2D workstation in SE2, like we have our state, X, Y, and yaw angle of the vehicle in 2D, and we have our control input, throttle and steering command. And the forward gear dynamics, as we have learned before, should be pretty easy for this very simple environment, right? So we take the current action, current state, we can predict the next state. And the goal here is to avoid the obstacles rather than driving on top of it, right? We want to do obstacle avoidance. This is the problem we are dealing with on vertically challenging terrain. So state-based is no longer SE2, now it's SE3. Then, unfortunately, our control input is still very limited, still the throttle and steering command, nothing more. But now we need to actuate the 6-off vehicle state. So X, Y, Z, roll to yaw in SE3. And then our forward dependent function also becomes more complex. It does not only need to take into account the current state at C, current action UT, but also the current environment. For example, the map, the elevation map underneath the vehicle showing red here, which we call MT here. We need to reason about that in a forward dynamics fashion. So this is quite straightforward if we want to read it in SE3 while leveraging what we already know the best. So this is our first approach based on decomposition. So we know how to model these 3-dimensional fixed-off state space, X, Y, and Y. We can use optimal theory or differential drive, any model, or favorite 2D model. We know how to do this very well. Then in addition to that, we just add 3 more components on top. For Z, we take the elevation map value onto X, Y, and we also take the roll and pitch angle based on the terrain path. We got NT here, based on the X, Y, and yaw angle, we can plot that onto our elevation map. And using the neural net to predict what is going to be the roll and pitch angle for that particular X, Y, and yaw. So then we design an SE3 cost function to the planning. We need to minimize the cost of rolling out the vehicle because that happens very often. We also need to minimize the cost of immobilization, being stuck by a large rock in the middle. We also want to penalize the too large height changes because vehicles won't be able to climb too much in one time step. Then those are the normal things, cost of going out of map boundary and also cost of estimated distance. Then using this, we can produce the path as a global planner. Then we simply track the global path using a simple PID control, right? How does this decomposed model work in a 4-bit kilo-dimension setup? So works decently well. So as you can see, we compare it against the behavior cloning EC model shown in red here on both our 4-wheel, 6-wheel vehicle and also 4-wheel vehicle. So our WMVCT is our virtual Chinese terrain is our decomposed model with a like 70-based motion pattern and our SC3 cost function. As you can see, our model is performing better than end-to-end behavior cloning learned on the same training set. But we use the training set to learn the full training dynamics rather than end-to-end policy. And you can see the green lines for roll and pitch has a smaller amplitude on both the 4-wheel vehicle and 6-wheel vehicle, meaning we have a more stable chassis while achieving higher success rate. So this 6-off decomposition works pretty well from the video we showed in the last slide, right? So we decompose into X, Y, yaw, and Z, and roll and pitch 3 parts. So the pros are pretty obvious. So it's very simple, it's also very efficient, and the very cool thing about this is we can actually parallelize roll and pitch prediction for predetermined terrain patches based on fixed X, Y, yaw. Because X, Y, yaw are based on argument, we can predetermine that very easily. So then, because we need to run everything on GPU with a very small vehicle, this can be parallelized, very straightforward. But the cons are also very apparent as well, right? Because we are dealing with vertically inclined terrain, X, Y, yaw do not really follow the argument steering model. An error in the argument steering model will also propagate into the error in Z, roll, and pitch. So now we're accumulating error by a lot. What we really want to do is we also want to bring in modeling of the X, Y, and yaw for vertically inclined terrain into our model. Don't just use a simple argument steering model anymore. So X, Y, yaw, in this case, are no longer predetermined because we want to model as not an argument steering anymore. And we need a way to quickly attend to the next terrain patch based on the last state action transition for the next model query. Because we need to run everything on board a very compute constrained small vehicle system, right? With this, I want to introduce our work, which will be presented tomorrow at this IROS called Terrain Attentive Learning, or TAL. Right, so we use self-supervised learning approach to enable this. On the left-hand side, you see the terrain attentive learning, self-supervised upstream pre-training. So we have elevation map. We also can randomly sample different X, Y, and yaw. That will give us a corresponding terrain patch correspond to that X, Y, and yaw. Then we use a self-supervised learning approach to learn a map encoder, a terrain attentive encoder, and terrain patch encoder to reconstruct the terrain patch. So the map encoder will give us our latent space representation for the map, and our terrain attentive encoding will give us a representation of GTA. We'll take the dot product, which will give us the MT, which is the representation of the terrain patch, and then we can decode it. Then we train all these 3 encoder and decoder in the end-to-end manner. Then during deployment, this very large map encoder only needs to be queried once every time the map is updated, so maybe 1 or 2 hertz, so very efficient. Then all the small models on the lower part, in the red circle, in the red box, are more efficient. So we freeze this terrain attentive encoder because it's already pre-trained on the map. We only need to train 2 other small models, which is the state action encoder and the kinodynamic model we can produce in the next state. In this way, it can be super efficient because we are not really counting on querying the large map encoder every time when we query the model. We only query the map encoder once when the map is updated, and we can query all the parts in the red box many times, thousands of times during real-time planning and sampling planning setup. So how does our model accuracy work? So here we show much better modeling accuracy compared against our decomposed WMVCT model. So green versus red. So you can see one state average 6-off error is much lower, the green bars are shorter. And on the right hand side, you see the prediction error with respect to prediction stats. So the red one goes up pretty quickly and with a larger variance, but the green is relatively flat with a smaller variance here. So on the lower right, you see a quantitative illustration. So you can see the green model, which is our core model, follows closely with the blue branches, while the decomposed red WMVCT model starts to diverge very quickly after prediction stats. So how does this high accuracy work on a physical robot? We integrate this with our NTP again on the rock test bed on the right. So one interesting thing we find out is that there's a mismatch between very high model query, model accuracy and a good planning performance. As you can see, the table on the right. So our model, top model, does not really achieve much better performance compared to the decomposed VCP model using a simple sampling-based reinforcement map, right? So why is the reason for that? We have a few hypotheses. First, the slow convergence of MPPI model, MPPI planner with our top model. So there's a trade-off between model accuracy. You can predict the next very precisely, but you need more compute to achieve that, meaning you have a very slow query speed. So you have a limit on how many samples you can query in your MPPI, which is not good, right? So there's also this so-called quantitative versus qualitative QNX understanding. Sometimes I don't need to understand very precisely how good or how bad the QNX is. I just need to know this is good or this is bad, right? So sometimes qualitative understanding is enough, while we don't need to waste some compute on quantitative understanding. So this motivates us to do better, right? Can we do better with this? So instead of only sampling, limiting my sampling, for example, I'm sampling a lot on this white patch, which are large rocks, which is obviously non-traversable, and wasting all my compute on that. Can I bias the sampling so that I can sample the blue region on the bottom so that I can avoid the large, the white piece or the green piece on the bottom, so on the top, so that I can be more efficient, right? So this motivates the last one I'm going to talk about called traversable and non-traversable, or TNT, right? So the intuition behind the thing is we want to distinguish the potentially traversable from the certainly non-traversable ones. So this is the so-called quantitative versus qualitative understanding, right? How do we measure traversability of a vertically channel terrain patch P, right? If you put that in any current traversability estimators, it will tell you nothing is traversable. You cannot go anywhere because all these are rocks, non-traversable terrain. We designed three things to quantify the traversability of usually non-traversable terrain. First is based on load and pitch angles. You can use the neural net, WVCT, or you can just use the physics-based model using trigonometry. We also want to capture the velocity uncertainty in terms of the commanded versus the actual velocity. So given the terrain patch, how different it will be. If it's different, meaning less traversable. If it's similar, meaning it's more traversable. However, this function is not well defined because the difference also dependent not only on the patch, but also on the commanded velocity. So that's why we use a mean and variance uncertainty, in a more statistical manner to produce the mean and variance of the velocity difference. Same deal here for post prediction and uncertainty. Our intuition is if you can predict the post very certainly, that means it's very traversable. If not, less traversable. We also need to do this, mean and variance for this difference between predicted versus actual post. So then, very quickly go through the entire pipeline. We have the elevation map. We query, we sample lots of different patches P. We query our road and pitch model, give us the road and pitch traversability map. We query our velocity uncertainty model, which gives us the uncertainty mean and variance in both linear and angular velocities. And then our post prediction uncertainty gives us the post uncertainty in terms of x, y, roll, and pitch. Then we combine them together using different weight function to have our final traversability map. Then we can just predict that using neural net and regression model. So last slide, how does it work? By using TNT to bias the MPPI sampling, now we are able to save computation from sampling and model query on certainly non-traversable. And we want to only reserve the high precision top model query on potentially traversable terrain. Then we can figure out what's the best. That's where we enable quantitative understanding. As you can see on the table on the top right, we see the success rate by using TNT is much higher, and we achieve slower, faster traversal time. And our run pitch angles, both absolute and change rate, are much lower, much smoother. And we can also observe much smoother throttle in order to navigate the vehicle over this terrain here. The video on the lower right shows you the difference when we are using traversability estimation to guide the sample. So with this, I conclude both directions, so high speed of navigation and wheel mobility on vertically challenging terrain. And I would like to thank all our sponsors and collaborators from UT Austin, so Peter Don's group and Joy D. Biswas group. And of course, all these work are done by our students. It was very hard to make all this possible. Right? So I only talked about these two directions today. I'm happy to talk offline. We have other vehicle ability research in the lab, including we want to deal with perceptually degrading environments. Imagine navigating a mobile robot into a dark forest without any light, without any active sensors. So light is not possible, and how can you navigate in darkness with perception degradation? We also work on socially confined navigation, as I presented a poster earlier, to how to navigate public spaces with crowded human population. How can we get to the goal, being efficient and also being socially compliant? I'll be happy to take any questions.
Thank you very much. Big applause. So our time is almost up, unfortunately, so I give the audience the chance for one small question, two small questions. Go ahead. If you have an idea, what do you want to ask? It was a very interesting topic. I mean, when have you seen autonomous cars climb on rocks? One question? Yeah? Okay, then I have one small question for you. What is the most difficult, the hardware or the software in that case? Because you show us a vehicle that you completely developed on your own, 6 wheels not existing. What was more difficult, the hardware or the software part?
I would say, hardware part is mostly making it robust. That's the most difficult part because we break all the time. Software is to make it work.
Okay.
Yeah, different aspect of difficulty.
Yeah? All right. Good. Shizu is still around, so if you have questions for him, another big applause. Then you can grab him and ask him some more questions. He will be around, and you can grab him and maybe have a deep dive together with him.